pushing, and making it the geometrically happy shape of a sphere or near to it. But if we lower the temperature of this balloon, it begins to act differently, and it's not really because of the balloon itself, although I promise we will return to what's happening to our balloon. It's more about what's happening to the gas inside the balloon. Now, I've tested it, and you might just have to take my word for it, unless you want to stick around until I've emptied the dewar at the end. But when this dewar is empty, it can fit 4 to 5 balloons, depending on how big I blew them up, but 4 to 5. And there, without much work, it just fit 10. Now, that's interesting. That's at least twice as many balloons as it could if it were empty, fit inside of it. But the more interesting question is this. Is there still air in the balloons? Now, in order to fit 10 balloons in here while this dewar was empty, I would have had to go with the tricky answer of just popping the balloons or putting them in before I inflated them. But those were 10 inflated balloons that now are taking up very little space. But if we remove them from the liquid nitrogen, and we allow the heat of the room to return to them, you can see that the scientifically interesting question of whether there is still air in these balloons turns out to have the answer of
yes. Look at that.
yes.
Oops.
Now,
Poppy pops.
I confess to you that it is quite a shock to the system of the balloon to go into liquid nitrogen. And that's why a few of our balloons didn't make it through. Secondarily, maybe the yellow balloons are weaker. The red balloon held strong. And most of the balloons did a pretty good job. And that's because the reason they were able to fit in the liquid nitrogen was not because the air had left them, but because the air had condensed. Condensing is the opposite of boiling. It is when a gas goes to being a liquid. Air is 80% nitrogen. And when you put a little bit of 80% nitrogen into a lot of liquid nitrogen, you get liquid air. And liquid air does not take up very much room. We can prove that for ourselves by seeing what happens to liquid nitrogen. Liquid nitrogen is going to go into this empty, now no longer empty, coffee container, and it is going to resist being contained. And it's going to keep resisting being contained as long as there is still liquid in this container. And that's because the liquid in this container is doing what the liquid nitrogen is always doing up here on stage, which is boiling. But it's also, by boiling, it's turning into a gas. And those gas molecules take up a lot more room than the liquid molecules. In fact, they take up about 700 times more room than the liquid. So we would need a much bigger container to contain all of that nitrogen. And in fact, that is why you see that the lid of my liquid nitrogen thermos is not screwed on, and even if it were screwed on, the lid has a hole in it. We do not want any exploding thermoses up here on stage. That would be bad and for everyone. Now, as our liquid is boiling, you may notice, or you may have noticed as we poured it out, or during any other of the experiments that we've been doing, that there's all this stuff. You might be tempted to call this nitrogen. But I'll tell you, this is not nitrogen, and in fact, it's not even gas. This is water. There's water in the air, water vapor, and those water vapor molecules will condense when they are close to something very, very cold, like the bottom of this coffee canister. And I can prove to you that it has nothing to do with the liquid nitrogen because there is no liquid nitrogen. It's all boiled off, it's gas nitrogen in the room now, and all that's left is a very, very cold coffee container. Now, the liquid nitrogen behaves very differently from water. And that's because water likes to be liquid at room temperature here on Earth, and liquid nitrogen does not. So if I were to dip this paper towel in water, it would soak up the water, and then it would just stay wet. Even if I just left it on the counter, it would stay wet until all of that water had evaporated away. Now, evaporation is not the same as boiling. While it is still a change between the same states of matter, the water in a paper towel is evaporating away. The liquid nitrogen in this paper towel is boiling away. And there's a difference. Boiling can only happen at a certain temperature, and it happens to all of the liquid. And as a result, it leaves this paper towel dry as a bone. It doesn't get things wet because it can't stick around as a liquid. It boils because this paper towel is as hot to the liquid nitrogen as a hot coal. You're not going to have liquid water soaking into a hot coal. You're going to have liquid water boiling off of a hot coal, and just like that, it boils off of our paper towel. And in fact,
That's cool.
liquid nitrogen behaves like water does compared to very hot things, because compared to liquid nitrogen, this pan, which was previously room temperature, is getting slightly cooler now, is as hot compared to the liquid nitrogen as a pan that's been sitting on the stove. As a result, the liquid inside exhibits some strange behavior that is reminiscent of a certain effect called the Leidenfrost effect. Leidenfrost effect makes the liquid inside look really weird. It sort of looks amorphous, looks like an amoeba that's sort of skittering around in there. And that's because the liquid nitrogen is being protected by its own gas. Some vapor forms around the liquid droplets, and they allow the liquid droplets, as long as I move the pan, to stick around for longer than they would otherwise be able to. If you were wondering, that is also why I can do this. My hand is protected by the Leidenfrost effect as long as it's moving quickly. But not everything is going to be protected from the liquid nitrogen. If you leave something submerged in there, it will be affected. We saw those balloons get affected, and you may have been asking yourself what was happening to the balloon itself. We're going to investigate that in a few different steps. One is by first investigating this rubber tube. It's stretchy and flexible, but that should not deter you from remembering that it is still a solid. It's just a flexible solid. But a solid has structure and shape. It does not drip or drop or roll away in pieces because it's solid. Other examples of solids include rocks, usually, ice, your bones, all kinds of things. But as we cool this rubber, we get it actually pretty close to liquid nitrogen temperatures, it begins to act differently. Now, you might be tempted to call this frozen. It's not frozen. Or rather, it was already frozen. It's just still frozen. Any solid is frozen. Freezing is the transition between liquid and solid. If it is solid, it's frozen. Those benches you're sitting on are frozen. They just happen to freeze well above room temperature, so we don't think of them as frozen. But this was already frozen. That doesn't mean it didn't change its behavior, though. And it changed its behavior in a way that is dependent on the fact that that is a polymer. Polymers are solids that are made up of long strands of molecules, like the rubber in that hose or in this ball, or the latex in the balloon, or your skin. This is a ping pong ball. It is not made out of a polymer. So by removing what we call thermal energy, meaning molecular motion, the energy of molecular motion, from any material, you are going to affect it. It's going to be affected, and it's going to be affected pretty intensely. And that's because all molecules have a temperature, and all molecules will be affected by a change in their temperature. Rubber molecules, for example, become pretty hard and brittle when they are exposed to low temperatures. Now, it's not heavier, even though it might sound heavier, it's just harder. It's undergone something called a glass transition, or hollow, it would probably have shattered. The ping pong ball is not a polymer, it's a plastic called celluloid, pretty dangerous and flammable plastic, actually. That has nothing to do with this. But as a plastic, it is relatively unaffected by liquid nitrogen temperatures. It probably would still be affected to some extent if we measured it really closely. And it is affected, but it doesn't stop bouncing. because quickly it returns to room temperature and it begins to behave the exact same way it did before. So now we have the question of the balloon. What happened to the balloon? Well, the same thing happened to the balloon as happened to that rubber hose and rubber tube, rubber ball, which is that it underwent a glass transition. It became a lot more fragile, a lot more breakable, but because I didn't exhibit any trauma on the balloons, they mostly came back to normal. This balloon, on the other hand,
Wow.
by hitting it, we proved that those latex molecules, which had undergone a glass transition, were no longer stretchy and flexible like they are at room temperature. Instead, they became brittle, breakable, more like an eggshell or a light bulb than a balloon. But quickly, those thin pieces of latex returned to room temperature. Now, it's not very good at being a balloon anymore, and in honor of Valentine's Day, I have a flower here. Now, the thing about this flower is that it is not made out of rubber or latex, but the things that living materials are made out of, cells, have a couple of important factors. The most important factor is that all life on Earth has cells that contain water. Now, other liquids get smaller when they freeze. Water is a polar molecule, so it gets larger when it freezes. And as a result, things containing water, when they freeze, if they don't have enough room to contain that expansion, they will burst. Now, if we were to do nothing else to this flower, it would return to room temperature, but it would be wilted and limp. We'll see that effect on the leaves and the stem, but it wouldn't be Valentine's Day if we didn't have a few broken hearts. So, the petals of the flower froze. They did freeze. And that's not because the petals themselves froze. It's because there was liquid water inside of those petal cells. And that froze. That had an effect. In case you're wondering, that is what frostbite is. So, we have been experimenting with all manner of material up here on stage. But you may not have noticed, because I didn't really call any attention to it, that most of the materials we have been experimenting with have been at room temperature. As a result, we saw some effects, but we would see a bigger effect if we were to, for example, experiment with something that was at a higher temperature than room temperature, like this previously boiling but still quite hot water. Because it is at a higher temperature, this water has more thermal energy. The molecules of this water have more energy. As a result, they're going to have a bigger reaction when exposed to the cryogenic temperatures of liquid nitrogen. In order to capture that reaction, I've put some average everyday dish soap in there. I promise, it really is just normal dish soap. There's nothing different about it. It's just dish soap. But before I do anything else, I'm going to tell you that we call this experiment the volcano. The volcano is pretty cool and fun, and I like it a lot. But I'm going to ask that if you like it, which I hope you do not try to rush the stage. Please stay seated where you are for just a couple of seconds. I'll change our slide and bring the lights down. That's your sign. If you would like to ask me some questions, you can come closer and ask me some questions. But please stay where you are until that happens. Because before we do any of that, we have to have our volcano. So, from a countdown of 5, 4,
3, 2, 1.
Oh my gosh, look at that. No, you can't go anywhere. Look at that. Cool.
all right. Thank you very much. Please enjoy the rest of your day.
Yay!